Being on the science and debate side of TikTok, I hear people make a lot of claims about space, radio signals, and vacuums, and very often they have never tested, measured, or personally investigated any of it. One claim I've heard is that radio communication in space is impossible because radio signals cannot travel through a vacuum. Some people even claim that light can't travel through a vacuum. So instead of arguing about it, I'm going to perform actual experiments. So here I've got my vacuum chamber. We're going to put a radio transmitter, a GPS receiver, several sensors, and a flashing blue LED inside the sealed mason jar inside of the vacuum chamber. The equipment inside of the jar will continuously transmit live data through the glass jar, through the vacuum chamber, and then to the receiver that'll be on top of the lid. We'll see whether radio transmissions continue, GPS receiver maintains a satellite fix, or whether we can see the flashing light. Now, some of you are probably thinking, but Debunker, we already know radio signals and light can travel through a vacuum. You would think that, but there are some people who confidently claim otherwise.
Radio signals cannot travel through a vacuum without a medium, okay?
So we're testing some stuff. Radio waves and visible light are both forms of electromagnetic radiation. Unlike sound, they do not require air or another physical material to carry them. I already expect radio and light to continue working, but knowing what should happen is not the same as showing it experimentally. So let's test it. This is the sender unit. It's an ESP32. It's this exact same type. It's just flipped this way so that wires are accessible. But it's just a pretty cheap ESP32. I think 3 of these was like $12. Then connected to it is this LoRa radio module. LoRa is a type of long-range radio communication. So once every second, this module sends a packet of the sensor data to another receiver outside of the chamber. Then this here is a GPS receiver. That's the antenna for it. Before beginning the chamber test, I'm going to position this near outside so it can get a signal. Now, GPS is only a secondary part of this experiment. GPS signals are extremely weak, so by the time they reach Earth's surface, roof, a wall, poor antenna positioning, any electrical interference, so sometimes these wires might mess it up, or obstructed view of the sky can cause the receiver to lose signal. But if it maintains signal, that'll be a good little extra bit of information we get. Then we have hidden in here a BME 280. This measures temperature, pressure, and humidity inside the mason jar. So it's going to be inside the mason jar, and it's really so I can measure what vacuum I'm pulling into the jar itself, and I can see if there's a leak happening. Then down here, it's as far away as we can get it from everything, is a 3-axis magnetometer. This measures the strength of Earth's magnetic field along 3 different axes. It's not central to the radio equipment at all, but it's recording additional data just in case anyone's interested in it. And finally, the little blue blinky LED. The LED flashes once every time we send data to the receiver. And it's really only there for visual confirmation, and because, like I said, it's kind of weird. Some people say light can't travel through a vacuum. So we have that. So this is our receiver setup. This will go outside of the chamber, and it's a ESP32 again, but this one has a built-in screen so we can monitor everything happening with this setup here in real time. So it's got packet number, how many packets we've missed, the time that's gone. This is the RSSI, which is like a signal strength. S is signal to noise ratio. Then we have pressure, that's in HPA, hectopascals. The temperature, currently, so this BME, if I hold my finger on it, you'll see that temperature climb up. So it went from 85, 88, 89. And then GPS, and the GPS isn't getting anything because I'm in my office. And because we know that this is sending data once every second, that's how we can see how many we're missing. So this is counting up one time every second it's sending something, and this is saying like, hey, we got 405 or 406, which means we missed one. So what we're gonna do is power both of these on and let it sit for the first 5 minutes. So as you can see, that is plugged in. This is plugged in and it is receiving data. We're gonna let this sit for 5 minutes. You can see the timer in the top right there. And just to gather essentially some baseline data with the lid off, the ambient air pressure and all of that. And then after about 5 minutes, we're gonna put the mason jar lid on the mason jar, then hook this up and pull a vacuum in the mason jar to about 600 hectopascals, so that when we make a full vacuum in the vacuum chamber, it's less pressure of this glass jar because we don't want to explode it. And something I didn't mention is this pad down here. You can see it through here. That is just an anti-vibration pad. It's mostly to keep it so that any vibrations from the table, the vacuum pump, anything like that, kind of lessens the effect from all the data. Okay, as you can see, that's about 5 minutes. So we're going to put the mason jar lid on here and then pull a pretty good vacuum. So I got to do this multiple times because this syringe isn't massive. But we have to unscrew this, or open the valve, pull some air out, seal the valve, and then pop this off and seal it, and do this multiple times. So we'll check what the air pressure is. I can kind of tell when this handle pulls back to try and the vacuum in the mason jar. I'll show you on this one. So we open the valve and then I pull this up, and when I let go, it just wants to pull back in there. So we are creating a decent vacuum in the mason jar. And like I said, this is just to, really, I don't want to pull a complete vacuum with all the electronics. That's the main reason why this is happening. And we can do kind of multiple things with it. We can see a partial vacuum, and then as a little bit of a vacuum, and then a big vacuum pull, and do these things go through both of those. So this might be the last pull of things. And we want to get this down to about 600 hectopascals, maybe a little more. What are we at? We're at 600. Okay, we'll leave it there. So seal this up, double check that, pull this, and then leave this here for about 5 minutes to get data. And what we're gonna see though, is we will see that temperature go up. I mean, it's already super hot, I'm in Phoenix, but we will see the temperature climb. And that's because we have a battery and a few modules and a light, and they're all just creating a little bit of like heat every so often, or as they run. So we might see this thing climb up to like 108, 110 degrees overall. And the pressure might increase a little bit because the heat is increasing, but it shouldn't go up entirely too high. And we'll leave this going for 5 minutes or so. Okay, so it's been going for a few minutes. We've got the P950 zoomed in so we can see the numbers there. But it's at 107 degrees, so it's definitely climbing. The pressure's gone up a little bit, but essentially, we're just going to turn this bad boy on, start pulling that vacuum, and see if we maintain. The big thing is keeping the, making sure we have the radio signal still coming through, but also GPS. We are at negative 20 inches of mercury right now. And it looks like we can still see red and blue passing through it, but we'll leave this on and just let it keep pulling this vacuum and see what happens. So we've been letting this go for a couple of minutes, and it looks like it's 29 and a half, negative 29 and a half inches of mercury. So I'm gonna close that valve, kill the pump, and we will leave this here for, say 5 minutes and collect the data. So it's been running for just about 5 minutes. We're still at negative 30. We have actually gone up in temperature pretty substantial, and the inside of the mason jar has gone down in pressure. That could be a small leak in the mason jar, but as you can see, the red and the blue light are still visible. So we might do a lux test sometime and measure magnitude of the light, how much light is shining through. But we can tell that light comes through mostly a vacuum chamber, and we're still receiving packets. We'll look at packet loss and see, did we get a substantial drop once we pulled the vacuum? But we're receiving packets. So radio waves go through a vacuum as well. And this is always fun. So we can go and release it. And just for funsies, I'm gonna open this valve and we're just gonna watch this thing. So we got back to the normalized air pressure, and it's still hot inside the jar. Which actually, when I feel it, the jar is pretty hot to the touch. But yeah, all our data's coming in. Now that the experiment is finished, we're gonna look at the data. This complete spreadsheet will be public because we don't lock science or data behind paywalls and charge you $200 for a thumb drive. If you know, you know. There will be a link in the description, and assuming I remember, I should put it in a comment or pin a comment. You can download the original data, make your own graphs, check my calculations, or anything you want with this data. It is public. So do not take my word on anything. Do your own tests, double check, verify. No blind faith here. So we recorded data for 20 minutes and 17 seconds. During that time, the transmitter sent 1,218 pings. We received 1,116. We lost 102 total. So that's a packet loss of about 8.4%, which is actually really good considering when I was just doing desk tests, I was always at 10 to 12%. More importantly, the radio signal never stopped. Packets continued arriving while the mason jar was open after it was sealed, and while air was removed from both the mason jar and a heavier vacuum within the vacuum chamber. We held about a negative 30 inches of mercury the entire time. So this is what we gathered as data from inside the mason jar. And like I said, most of this was just for fun. The real test was light and radio signal, and a secondary GPS, which if we look at it, we got the GPS signal the entire time. We actually ended up over time, which happens in real life when you go out into the sticks and hike. When we first connected to the GPS, so we turned it on, it took a second. Then it connected to the GPS and had 8 satellite connected. And then as time went on, it got 9, 10, 11 to 13 or 12. I can't count. I can't read numbers. 12 satellites connected, which happens in real life when you go out into the sticks, turn on your GPS. It doesn't start as strong, and as time goes on, it connects to more and more, as long as it can see them up in space in the sky. So here we go, though. When we first started, we had about 966 hectopascals, and then you can see as we pulled, each time we pulled the more of a vacuum with the syringe, and that little jump there, that is actually when I pulled, let me expand this weird little down hiccup down. That's when I pulled it and then let go so you could see it vacuum back down, and then kept pulling. So this is the 5 minutes that we left it just sitting there, not doing anything. We can see that very slight pressure increase, 599 to 605. That is because temperature right here was increasing the pressure. But what's fun is we can see this temperature is still going up. When I pulled the vacuum within the vacuum chamber, there must have been like a tiny leak or something, because it dropped pretty quickly and then it started to like level out. So I'm pretty sure there was some type of leak, and it's probably because those little valves that I have were like 20 valves for $6. So they're not exactly lab grade. So then temperature results, as expected, the temperature climbed pretty much the entire time. And this is because it was in a sealed mason jar, or slightly leaking mason jar, with a little battery pack. There was a battery pack, there was the ESP32, and three sensors, an LED light, a resistor that heats up, and then the LoRa module. This is the strength of the LoRa signal, the radio signal. If we look at the RSSI, which is the blue line here, that measures strength of the signal received. A number closer to 0 indicates strength, so pretty much the higher this line, the stronger it is. During the entire experiment, the RSSI range, it pretty much went from like -21 to -38, was like this hardcore spike down here, right at the end of the test. So that's probably right when I was like messing with everything, closing out the test.
The average set at -25, which is pretty much right along where this flat line is. So this is a small change, but several things changed simultaneously. The transmitter was moved, the orientation changed, I was moving it around. The pump and other electrical equipment operating nearby could cause fluctuations, like clicking on the vacuum pump could cause a spike, stuff like that. And then the red one here is signal to noise ratio. It remained between 8 and 12 throughout the entire recording, which its average was about 10. There's no collapse in signal quality when the chamber was evacuated. During the atmospheric baseline, average signal to noise ratio was pretty much the same. So we can see it here, and then it just kind of hung out the whole time. There were spikes, of course, but you got to remember too, every second. So like this big flat line, it was the same the entire time through there. And then it had a little tiny down spike. So the signal remained clearly distinguishable from background noise throughout the entire test. Now for packet loss. This is the important one. The receiver recorded 102 missing packets over 1,200 attempts. A little over 1,200. You can see that here on the graph. It increased a tiny bit here, but we can't isolate that change strictly to pulling the vacuum. There's moving the equipment, again, moving everything, turning on GoPros, my cell phone, the camera, the pump to the vacuum chamber, random cars driving by. This is also a really short range. I mean, this was only transmitting about a foot away with a very strong signal. So these signals should reach, with these cheap LoRa modules and that tiny little gold antenna, they should reach about 5 miles. So 1 foot is very close for a very strong signal. The important observation is that we kept receiving packets the entire time, no matter the pressure change. It didn't create some radio blackout. And now this data here, these 3 columns, this is the magnetometer. We recorded it throughout the experiment. Most of its values remained relatively stable. There were some large changes when I moved the jar or manipulated any of the equipment. We can see one of the big drops. It was in like the hundreds, and then it dropped down to the 70s. And this was right at the 5-minute mark. So this was when I put the lid on the mason jar and was pulling the vacuum. So you can kind of see it dropped, and then once I quit messing with it, it went back up. And it's really just because my hands are near it. And we introduced a metal lid about 6 inches above it. So we saw some changes, but nothing drastic. So we know Earth's magnetic field stayed the same. And the blue blinky LED light, we saw that it still worked, and the red light, we saw that they still worked the entire time. So what did the experiment show? It showed that LoRa radio transmitter continues sending data throughout the entire test, and GPS signals still go through vacuum. The signal remained strong pretty much the entire time. The GPS never failed. The lights were visible. The mason jar was our only thing. It seemed to have a small leak. I'm not going to hide and pretend that this setup was perfect. This was an experiment, and experiments do what they do. If you've ever experimented anything, you know that. This is why I record all the data and make everything publicly available for every experiment I do. I always do experiments that pretty much anyone can double check, verify, or do themselves. And anything that has data, I try to make publicly available. But the primary question has an extremely clear answer. Do radio signals require air as a medium? No. Lowering the air pressure didn't stop the radio transmission or the GPS signal, and that is exactly what established physics predicted would happen. That claim, radio signals can't travel through a vacuum without a medium.
Radio signals cannot travel through a vacuum without a medium. Okay?
I put a transmitter in a reduced pressure environment, surrounded it with a vacuum chamber pole of negative 30 inches of mercury, and continuously received transmission outside. You don't have to trust NASA. You don't have to trust me. You can watch the experiment, download the data, check it yourself, or perform your own version. That's the difference between repeating a claim and testing one.